1, 2, 3, 4. Circles. She's spinning me around in circles again. Oh.
Hello, Dr. Doherty from ACU Physics. Let's talk about rotation. So now it's time to address what happens when things spin and roll. All we're going to do is review basically everything we've covered so far, but for rotating systems. So we'll start off with the definitions and the kinematics for now, and then in part 2, we'll talk about force, energy, and momentum. So this is covering what we've done before, but extending it to something new, so it should be a good way to learn and review at the same time. So we got to talk about radians. It's finally time to switch our calculators from degrees to radians and live there for at least the rest of this video series. We're going to use radians because they help us, because they make life easier, not harder. So this is why we put up with it. They're a really natural unit because they're based on the circumference of a circle. So we have a nice definition here for arc length that really controls everything. So I have some angle theta measured in radians for a circle of radius r, and then so I have an angle theta for a circle of radius r, and s is this arc length, the length of this pi wedge going around the circumference of the circle. And we have a really nice equation that only works in radians, that theta equals s divided by r. Okay, so now this gives us a good way to think about radians. So you know that for one full lap around the circumference of a circle, that's 2 pi r in distance. So theta is 2 pi r divided by r, which is just 2 pi radians. So there's 2 pi radians inside the circle. It really makes life easy to deal with. Now to convert back and forth from degrees, just remember that 2 pi radians is 360 degrees. So we can divide or multiply by doing unit cancellation, and we can show that 1 radian is about 57 degrees. You should know how to convert back and forth and be comfortable with that. All right, so now I'm going to measure my angle theta in radians. Let's see how far something goes. So we'll just define an angular displacement. So delta anything in this class means a change, so delta theta means a change in theta. So I start at some initial theta, theta naught. I end up at some final angle theta, and the difference between those is delta theta. Now notice though we have this drawn, there's a really important definition here that we can't get wrong. Angular displacement, based on graphs like this, is positive if it's counterclockwise. So if I start here and increasing theta makes me move this way, this is the counterclockwise direction that this arrow is showing. If I'm going this way around, my delta theta is negative. You've got to get those signs right to get the right answer. So in the same way for linear things, we say positive is going right or going up, and negative is going left or down. We say positive is counterclockwise, negative is clockwise. So now I've got something that's turning. Well, how fast is it turning? Okay, let's define an angular velocity. So we've been using the letter v for velocity. So now we're just going to switch everything over to Greek letters for our angular things. So we're going to use this omega. It looks kind of like a W, and W is kind of like V, so we can remember it that way. But otherwise, the definition is identical to what we did before. In linear things, velocity was displacement over time, delta x over delta t. Well, so now in rotation, omega is delta theta over delta t, displacement per time. That's going to give me units then of radians per second. Okay, what if my velocity changes? Well, then we just need an acceleration. We've been using a for acceleration. The Greek letter a is an alpha. Looks a lot like an a, so it's pretty easy to remember. Linear acceleration was change in velocity over change in time. So this is just change in angular velocity over change in time. It's going to give me units now of radians per second squared. As always, paying attention to units makes everything really easy. So now we get this very, very simple map, like a recipe for making angular equations. This is our Rosetta Stone for going between linear and rotational things. All I have to do, and it really is this easy, I take all my x's, I replace them with thetas. I take all my V's, I replace them with omegas. I take all my A's, I replace them with alphas, and I'm done. That's it. Everything just works. And we'll talk about the rest of the quantities in part 2. So what I can do is I can take the big 4 equations for accelerated motion, these guys over here that we're pretty comfortable with by now, do this little transformation, write them in fancy Greek letters, and I get these equations, and they just work exactly the same. Everything is exactly the same. The only last idea to talk about is how do I relate rotational things to linear things? And all we have to do, again, is just pay attention to units, and things will work out okay. So this diagram, I think, helps to explain things. So I've got this line of people. Here they're figure skaters because normal people don't walk and turn in straight lines. So I've got this guy here in the center of my circle who's rotating, and everyone is following a line around him. We can tell from common sense that the people on the far edge have to be moving really quickly, while the people near the center are moving very slowly. But that moving is the straight line linear velocity. Now if I draw out the path of this guy's circle over here, what I see is his velocity at any moment is tangent to the circle. So that's a straight line touching the edge. So we're going to call this a tangential velocity. But that's just a linear velocity like we've talked about for quite a long time by now. And if that velocity changes, I could define a tangential acceleration. So let's now relate this straight line linear tangential velocity to an angular velocity. Okay, diagrams and units are all we need. So if I go and I think about, well, the distance he travels from our radians equation is going to be r times theta. And if theta's changing, the rate that that's changing is omega. So the rate that my distance s is changing is just going to be r times omega. So for tangential velocity, omega's got to be in radians per second. Now the units of tangential velocity are meters per second. So look at the units here. Meters per second equals meters per second. The radians don't really count. We kind of treat those like a number. So I don't think of meter radians per second, just meters per second. That's it. Multiply omega by r, and I've got my tangential velocity. Same thing with the acceleration. Let's just think about units. A is meters per second squared. Alpha was radians per second squared, but radians are just a number, so I'm going to ignore that. So I got to have meters per second squared equals meters per second squared. So easy if we just think about units. Now, one really nice application of these is thinking about rolling. So let's talk about a wheel now that's rolling, and we have to say without slipping to be accurate here. The distance the wheel rolls is equal to the path length around the wheel. So that is, if my wheel is going to go from point A to point B, the distance from A to B is the same as the distance around the wheel S from A to B. And the equations for rolling are exactly the same as we've worked out before for tangential velocity and acceleration, r omega and r alpha. So I can connect the car's speed, v, to the angular velocity of the tires, omega. And then I could do all the kinematics equations to know everything that I need to know. One last definition for us, and then we're done. If I think about centripetal acceleration, so in the uniform circular motion video, we talked about if an object is moving at a circle at a constant speed, it's got to have an inward force. And centripetal means center seeking, so an always inward going force. And that was defined as v squared over r. That's a tangential velocity. So if I plug in that v is r omega, I can cancel out one of these factors of r and get my centripetal acceleration is r omega squared. Now if I really wanted to, and I'm not sure that we want to, but if I really did, I could combine my centripetal acceleration here with a tangential acceleration that's going to be r times alpha, and I could get non-uniform circular motion. something that's rotating and speeding up or slowing down at the same time. So we have the power to solve more complicated problems just by paying attention to these unit conversions. So that's going to be it for part 1. The whole idea is this Rosetta Stone. I take my linear quantities, x, v, and a. I replace them with my Greek letter rotational quantities, theta, omega, alpha. And I can just reuse all my equations without having to think. It's really easy to do. And then point number 2, pay attention if you're given an angular or a tangential quantity. If I'm thinking about speed, am I thinking about your linear speed in meters per second? Or am I really thinking about like an angular speed in radians per second? Those quantities are really important to not get confused. Now the units tell me I can just multiply or divide by r to make the units work out every time. All right, and in part 2, we'll talk about force, energy, and momentum. Thanks for watching.
Something about the ages. I failed college algebra again. That skinny blonde girl, and the circles, and the ages, and the ages. Beautiful.